Now I'm being a bit lazy, I still haven't sat down and thought about it. Maybe it is blindly obvious, but not to me. Anyway, so again I throw it out, this happened before, right? So I throw it out to you as a brain teaser. Condition 3, remember, what is that? The length of xy is less or equal to p, little p, the pumping length. Okay, that's condition 3. And from that you deduce that y can, for this problem, can only consist of zeros. So go figure, right? All right. Now, so now we're going to examine whether it seems a bit of a this is not pumping down, it's pumping up. But anyway, so now let's go look at a mildly pumped up string x, y, y, z to see whether it belongs to the language E. And you'll see in a minute why we're going the other way from what the introduction was talking about, pumping down, because here we're pumping up. Well, okay, so you add an extra y, right? You've pumped it up mildly, so you have now just one extra copy of your y substring, and given what we just said before, that the y can consist only of zeros, well, that just means you've added more zeros to your string, so it still belongs to E. Makes sense? Right? By adding an extra y here, they're all zeros, so the number of zeros in your pumped string will be larger than when it was not pumped. So the number of zeros in this will be larger than the original string xyz, and therefore the pump string belongs to this language. It does belong to E. Well, that's not helping, is it? I mean, you're trying to refute the idea that E is regular. You're trying to show that E is not regular. So your pump string still belongs to the language. So that's not helping. So pumping up didn't help. All right. So so you don't get a contradiction. That's what I've been saying. Now remember the pumping limit here. The pumping limit says your pumped string. Here's the result. So you've now got I copies. I was saying this a bit earlier. You have I copies of y, but I is greater or equal to 0. So in other words, it can be 0. So your I could be 0. All right. Well, let's make it 0. So we're pumping down now. Okay, like I was talking about before. So now you got y to the 0. Well, that's just the empty string. So you're just left with x, z. Right. Now before we said that y can only, for this language, that y can only contain zeros. So that's a critical deduction in this proof. So y can only contain zeros. All right. And condition 2, I should mention, I don't think Sipser did, but anyway, condition 2 is that the size of y is positive. Right? It contains at least one y. It contains at least one zero, at least a single 0. Well, that means if you remove the y, given that your string xyz is of this form, okay, you pump it down, so you have removed at least one 0, a single 0 or more, from your string. Well, if you do that, given your S is of this form, and you remove at least one 0, well now you've got, then you'll have 0 to the p, 1 to the p. In other words, there are now an equal number of zeros and ones. In other words, it's not true that the number of zeros is greater than the number of ones, because that's the condition that that string, that pumped down string, belongs to the language E. Okay, so that means that this pumped down string, this here now, does not contain more zeros than it contains ones. Therefore, this pumped down string here does not belong to E. Okay? Well, you found yourself a counterexample. So you've got a contradiction. This string here contradicts what the pumping lemma says. Pumping lemma says that this string should belong to E, but it doesn't. We just proved that it doesn't. And therefore the original assumption that E is regular is false by modus tollens. We deduce that the original assumption that the language E is regular, that's not true. Therefore the language E is not regular. And we've proven the fifth example. That's the end of the fifth example. Now, just to I'll fill up a little. I've got 5 candidate books here on theory of computation that I might use in future courses. Some of them, I have a bit of a question mark. I might throw out one or more due to too much overlap between the texts. So I don't want to repeat too much. It's a matter of judgment, and I'm not sure yet. But some of them, complexity theory is pretty basic. So that, I'll get them in order. Hold on. So that would probably be so it's by Homer and Salman. All these texts you can get them for free on eMule. So I got five books I'm talking about here. They're all available on eMule. So this one on computability and complexity theory, I'd say that's probably senior M1 level. Now there's a possibility that the overlap with this and the Sipser book, when I get through the Sipser book, I may dump this because there may be too much overlap. Similar comment with this one. This is more an M1 level. Now I've used it. You can see it's sort of pretty used. This is the text I used in China when I was teaching it, and that was the course that my dean, Chinese dean, insisted. He was looking for more commercial reasons, I dare say. He wanted the seniors to be taught theory of computation, and I had a 1/4 dropout rate from those bachelor students. None of the master students dropped out, but that's well known. The theory of computation is the toughest course in computer science because of all the pure math. So that's the text I used, and towards the back here, the proofs are getting quite hard. But again, I'm not too sure how much of an overlap there is between this one and Sipser. So this too may get dumped. That's a possibility. Now on complexity theory, a major topic in theory of computation, that'll be part 3 of Sipser. So again, same comment. Now this one, computational complexity, another complexity theory. So As this one, it's by Papadimitriou, Greek name obviously. In fact, that is one of the co-authors of this one, also Papadimitriou, Christos. Yeah, Christos, Papadimitriou. All right. So this text definitely master's level, I'd say. But you know, it's a whole. How many pages is it? 500. Oh god. Well, I might even dump that just purely on length. 500 pages. You imagine how long it's going to take me. But on the other hand, complexity theory is a very important part of theory of computation. There's a lot of ongoing research in that area, and one of my personal interests, research interests, is the possibility of going beyond conventional complexity. Like, I think I've mentioned it once before, but one of my big hopes, big dreams, is by studying advanced math and physics, I might be able to come across phenomena, maybe nonlinear phenomena, in, for example, QCD, quantum chromodynamics, physical phenomena which has a complexity, well, yeah, I'll translate it into ordinary English, that these, one or more phenomena in physics, perhaps using phenomena in quantum chromodynamics, with quarks and gluons and stuff like that, that will allow me to compute with a greater level of efficiency, more power, computational power, than is possible with quantum computing. Now, with a quantum computer, if you have n, I've said this before, if you have n qubits or quantum bits in your quantum register, so just imagine a qubit here, like for example a spin on an electron. Say you have a whole row, register, a row of these electrons, and you're storing one qubit, quantum bit of information on